Okay, so let's do an example. So let's say I have a box that has a partition in the middle, and I have on one side 3 moles of H2 gas, and on the other side 1 mole of N2 gas. And if the partition's right in the middle, then I know that the volume of each gas is the same to begin with. So the H2 and N2 have the same volume. I'm going to call that the initial volume. And let's also assume that they're at the same temperature. So I'll call that the initial temperature. Now, how do the pressures compare? The volumes are the same, the temperatures are the same, but the number of particles is larger, 3 times larger over here. So we would expect more pressure over here. We'd expect 3 times the pressure. So let's see how that works out. So the pressure of the H2 gas, I'm going to be using P equals nRT over V, right? We're assuming these are perfect gases. So in this case, it's N of H2, R is a constant, T is Ti, and V is Vi. And we know that the number of moles of H2 is 3. So this is 3 RTI over Vi. The pressure of the N2 gas, number of moles, R, has the same temperature, same volume, and the number of moles of N2 is 1. So it's going to be just RTI over Vi. And so as expected, H2 has 3 times the pressure of the N2. And then this quantity right here, RTI over VI, you see it appears twice. So I'm going to call this just P. Okay. Okay, so using that notation, the initial pressure of H2, and that's actually what these were as well. The initial pressure of H2 is equal to 3P, and the initial pressure of N2 is equal to P. Okay, now we're going to remove the partition and let the gases mix. Okay, so we remove the partition and let the gases mix. So what's the new pressure? First of all, temperature, the new temperature, TF, is going to equal, well, they both had the same temperature to begin with. The temperature was already uniform, so the final temperature is not going to be any different. So if they were both at 25 degrees C, then the final temperature is still 25 degrees C. The final volume compared to the initial volume, well, each gas originally occupied half of the box, and now they each occupy the entire box. So both gases have doubled their volume from their initial volume. All right, so let's look at what the final pressure of the N2 gas is. So that's 1 mole times R times T final over V final. All right, we still have 1 mole of N2 molecules. That hasn't changed. V final is equal to 2Vi. T final is equal to Ti. So making these substitutions, I have RTI over 2Vi. And you recognize this quantity, RTI over Vi. I called that P. So this is P over 2, the new pressure of the N2 gas. It started at P and now it's P over 2. It was halved, which makes sense because its volume doubled and everything else stayed the same. All right. Final pressure of H2. Same process, 3 moles, RTF over VF, which is going to be 3 RTI over 2 VI. So that's 3P over 2. And so the total pressure after the gases mix, these, by the way, are the partial pressures now. Now these gases are part of a mixture, and this is how much pressure each gas contributes to the mixture. And so the total pressure is going to be the sum of the partial pressures. which is going to be 4p over 2 or 2p. Okay, now finally we're ready to calculate the Gibbs energy. So we're going to use this formula. G is Na mu A plus Nb mu B. And we're going to use the formulas for mu A and mu B that we derived earlier. Okay, so we're going to use this formula before mixing to find the Gibbs energy before mixing, and then use it again after mixing to find the new Gibbs energy, and then we'll subtract them and we'll have delta G. Okay, so G initial. So I'm going to use this formula here. So I have 3 moles of H2 times mu standard of H2 plus RT ln, and the initial pressure of the H2 gas was 3p, and the initial pressure of the N2 gas was p. Okay, so I'm putting pi in here right now for both of them. So this one is 3p plus the second term, 1 mole of N2 gas times mu standard of N2 plus RT ln of P. That was the initial pressure for the N2 gas. All right, so that's G initial. What's G final? So again, 3 moles of H2 times standard chemical potential of H2 plus RT ln, and now the pressure of H2. In this case, it's this partial pressure up here. It was 3p over 2. Plus, and then for the N2 gas, I have this, where the pressure of the N2 gas, the final pressure of the N2 gas is p over 2. All right, now, this is what we've been after the whole time, is I want to know what's the delta G. So I'm going to subtract G final minus G initial. And as we saw earlier, a similar situation, the mu standards are going to cancel when I subtract these two equations. And I'll be left with a bunch of terms that look like RT ln of something. So let me write that out. Okay, so first I grouped the H2 terms. So we have 3 moles of RT ln 3p over 2 in the final formula. And in the initial, it's 3 moles of RT ln 3p, which I'm subtracting because I'm subtracting G initial. And then I need to do the same thing for the N2 terms. Okay, so it's RT ln p over 2 minus RT ln p for the N2 terms. All right, and now you see that I have 3 RT ln, 3 RT ln. I'm going to combine these. This is a subtraction, so to combine these natural logs, I would have to take this argument and divide by this argument. So you can see that when I combine the natural logs, the 3p is going to cancel. I'm left with natural log of a half. Same thing happens down here. When I subtract this ln p from this ln p over 2, that's like dividing the argument p over 2 by the argument p. And so the p's are going to cancel. I'm left with ln of 1/2. So all of this simplifies quite a bit to 3 moles RT ln of a half plus 1 mole RT ln of a half. Now I'm going to rewrite ln of a half as ln of 2 to the negative 1. And since the negative 1 is an exponent, I can bring it in front. So I get negative 3 moles RT ln 2 minus 1 mole RT ln 2. And I can combine this some more. I'm going to get minus 4 moles. Go ahead and do it, because I have the same terms here. So combining these. And now I can compute the results. And this let's say the temperature was 25 degrees C. Then plugging in the numbers here, I get negative 6.9 kilojoules. Okay, so that was the change in the Gibbs energy when we mixed these two gases. I'm going to have you do a similar problem in the homework. Now, one important thing I want to point out is that this negative result here does not, even though this is delta G, this does not imply spontaneity in this case, because we did not hold P constant. And when I wrote this earlier, I should have added this in here, that dg less than 0 is a spontaneous change, but only if we hold P and T constant. Okay, that was our criteria for spontaneous change. We did not hold P constant in this case, in this example that we did. P changed. The total pressure at the end was 2P. The pressures of each gas changed. Okay, so we did not hold P constant. So the fact that this is negative doesn't necessarily imply spontaneity. Okay, the last topic I'd like to talk about is a couple of other mixing quantities. I want to talk about the entropy of mixing and the enthalpy of mixing. So in the previous, or a couple chapters ago, in section 3E, when we were talking about entropy, we saw that entropy can be calculated by taking a derivative of the Gibbs energy with respect to temperature while holding pressure constant. Okay, so I'm going to write this equation in a slightly different version. I'm going to write the left-hand side. I'm going to use delta mix S. And the argument here is that I could take this equation for S final, and I take the same equation for S initial, and I subtract the two. Then I get a new equation that has delta S mixing on the left. And I can make a similar argument on the right, where I'm going to replace G with delta mix G. And I can do that because of the same argument. Imagine I have these two equations, one with a G final, one with a G initial. When I subtract them, I'm subtracting the derivatives, but the derivatives are the same, d dt. So I can combine the arguments, and I end up with the derivative of the difference. To put that another way, the derivative of a difference is the difference of the derivatives. So I'm just going backwards. So the reason I want to write it like this is because we have a formula for delta mix G. And we can use that to find what the change in entropy is when we mix two things. So we've seen recently that delta mix G is equal to this. And so now I want to find delta mix S. Well, I take this, I put it up here, which means I'm going to take the temperature derivative of this. Well, the temperature only appears here, and so that's going to drop out, and I introduce a minus sign. So delta mix S equals negative NR times XA ln XA plus XB ln XB. Okay, so this is called the entropy of mixing. And this is for mixing two perfect gases. And once again, we can use this argument that xj is always less than 1, and therefore the natural log of xj is always negative. So these terms are always negative, and there's a negative sign out here. These are always positive here. So this negative sign and the negative in here cancel. And so that means that delta mix S is greater than 0. And this makes some sense. When we mix two gases together, we would expect the entropy to increase because the disorder is increasing. Okay, so I'm going to do a quick example. So if we have equal amounts of perfect gas molecules and we mix them at the same pressure, what is delta S? What's the entropy of mixing? So if we have equal amounts of the perfect gas molecules, then the mole fraction of A is going to be a half because it makes up 1/2 of the total number of moles. And same with XB, it makes up the other half. So XA equals XB equals 1/2. All right, and now I'm going to use this formula up here. So delta mix S minus NR. XA is a half, ln a half, plus XB is a half, ln a half. Okay. I'm going to add these two terms together, and I get ln of a half. And then I'm going to do what I did before. I'm going to write this as ln of 2 to the negative 1, bring the negative 1 out in front. And now if I know the total number of moles, I can find the entropy of mixing. So let's say we had 1 mole of each gas. All right, then the entropy of mixing is, this N is the total number of moles, right? So if we had 1 mole of each, then we have a total of 2 moles times R, which is a constant, ln2, which is a constant, and this works out to be 11.5 joules per Kelvin. So again, entropy increased when the two gases mix, as you might expect. Okay, so that was the entropy of mixing. Now let's talk about the enthalpy of mixing. I'm going to start with this equation for delta G, which we saw a long time ago when we first looked at delta G. It's equal to delta H minus T delta S. And I'm going to say that each of these deltas is a mixing delta, okay? So I'm mixing two gases together. And now let me solve this for delta H. So delta mixing H is going to be delta mixing G plus T delta mix S. All right, and see what we get. Delta mix G we saw was nRT XA ln XA plus XB ln XB. Okay, and delta mix S was very similar, except it was negative and it lacked a T temperature, which went away because we took this derivative here, right? And here I'm taking delta mix S and I'm multiplying it by T. So I end up with minus nRT XA ln XA plus XB ln XB. And these two terms are the same with opposite signs. So the enthalpy of mixing is 0. Now, why is delta mix G negative? So we can explore this very easily here. Going back to this equation, right? So delta mix H, the mixing enthalpy, as we just saw, is equal to 0. And the entropy of mixing is greater than 0 And so I have 0 minus a positive number. So that means that delta mix G is less than 0. And it's less than 0 because entropy increases. So in the case of gases that are mixing, entropy is what drives the spontaneity of the mixing of two perfect gases. All right, and I will end with that.